Hi, everyone. My name is Caralyn Reisle. I'm from the University of British Columbia, where I'm a PhD candidate. And today I'm going to be talking to you about this data set we've developed that is to support curation activities within the cancer knowledge base CIViC. For any of you who work in precision oncology, this is going to be a familiar workflow. We take patient consent, or we get patient consent and a biopsy to collect samples. That sample is then sequenced. And then there's a variety of bioinformatic analysis that is done to end up with a set of variants. Now, while a lot of this is automatable, once we get to the variant interpretation part, it becomes a lot less so. So the process of variant interpretation is largely manual, and therefore it's considered a bottleneck. What we use to address this is these cancer knowledge bases, which includes CIViC. And these are ways of having these structured ways of representing this data so that it's both human and computer readable. And this allows us, when we have a patient's variants, to automatically map them to interpretations of those variants, which we can then use downstream. Well, cancer knowledge bases address the variant interpretation bottleneck to a degree. Their creation is really time-consuming and labor-intensive. It requires a high level of expertise. CIViC, in order to get around this to a degree, has adopted a crowdsourcing model. And this enables rapid growth. However, to ensure that the accuracy isn't compromised, anything that's submitted to CIViC then needs to be reviewed by a small group of highly trained expert curators, which we refer to as editors. And currently in CIViC, there are more than 2,000 people with accounts that are able to submit content, whereas there are less than 40 people that are trained to do the review. This leads to a new bottleneck stage where more than half of CIViC content is currently pending review. We would like to use these fact-checking NLP methods, which have gained popularity in the last 10 years due to the spread of misinformation and in the more general fields. And we'd like to be able to use those to help prioritize problematic content in the CIViC knowledge base, as well as just look for human error and other sources of error that may occur. But how can we use this for CIViC? So many fact-checking automation systems follow this similar pattern where verifiable claims are identified in a document, and then we retrieve the evidence for the claim, usually down to a passage or sentence level. And then both the evidence and the claim is passed into a claim verification model, or often called stance classification, which determines whether the evidence actually supports the claim, whether it refutes the claim, or if it's insufficient to make a decision. The problem we have doing this for CIViC and for other cancer knowledge bases is that we're lacking an existing benchmark to really do this evaluation. So while there are fact-checking data sets that exist out there, most of them are general or political knowledge, like Fever or Feverus or PolitiFact. A lot of them are natural language only. So if we're going to do this on a knowledge base, what we're inputting is a structured claim. And many of these data sets exclude tables in the evidence or only include tables in the evidence. And we really need a mix of the natural language and the tabular data. Probably most significantly, almost all of these data sets, when they're on the scientific literature, only include the abstract. And from our early work, we've been able to analyze that nearly 2/3 of the evidence items or entries in CIViC can't be validated just reading the abstract. Finally, this brings up a problem that is going to be familiar for anyone who's been working with these large language models, and that is that long context input length creates its own issues where LLMs and other models tend to miss stuff in the middle or tend to make incorrect assumptions. And it's just computationally more expensive. So to address this, we've created this benchmarking data set of CIVic-Fact. And this is a companion data set to CIViC, the knowledge base itself, where expert curators went and, using the web tool hypothesis, we have selected the evidence level or sentence level evidence provenance and linked that back to the CIViC knowledge base. So this is really what we asked the curator to put here was what they would need to read from the paper in order to be able to verify that the authors did indeed say that. So this creates our claim verification data set. You can see on the right there, which has the structured elements from CIViC in as the claim. We have the selections done by the curator in as the evidence. And then the label is this evidence direction in CIViC, which is really important because CIViC not only curates positive associations, they also allow you to curate negative findings, where someone tested something and it did not show an association. Thus far, we've manually curated over 1,000 CIViC entries with this, covering nearly 600 different publications. But we also augment this data in several ways because this really alone isn't enough to train a model from. But even more importantly, if we're only training on the highly curated quality data, it's not going to pick up the errors. We need to show it what's wrong. So what we do is we modify the existing claims in several ways to using these ontologies that are pre-linked to use the wrong level of specificity, for example. Or we will use fully generated claims that we then pair to evidence and say, this is something that if someone entered that, that's wrong and it's off topic or just they've linked the wrong source. Many different ways that you can have curator error. Because this includes generated data, we have then done a downstream human evaluation of this data to make sure that these are valid on a subset. And you can see those numbers here. So what we've done both passage retrieval and the claim verification in this step. Right now, what I'm showing you here is on the left. This is the evaluation of these large language models and as well as encoder-only language models that we fine-tuned on the CIViC data set. If it says FT, that's fine-tuned. And on the left, we are using the gold retrieved evidence. And then on the right, that's when we're doing it as a full pipeline. And we've included passage retrieval models, which are selecting the evidence for us. So this is really a more accurate measure of how we would use this in practice, because it's not really practical to have somebody go and select all the evidence. And what you can see is that the best performing model is the Llama 3.1 8 billion parameter model, which we have fine-tuned. The encoder-only classifiers aren't that far behind, but the open large language models do not perform very well. I say this with the caveat that we quantize these models to run them on our compute resources, so it's not an entirely fair comparison. And if we could have run the largest open models, it's possible that they might have done a lot better. But with what we were able to run, the open language models aren't really performing that well unless you include the fine-tuning. The proprietary models do better, but still not really reaching the level of accuracy that would be helpful. So the next part we did was to actually apply this to CIViC itself and see if we could catch curator error. So we used our the best performing retrieval model we selected. We combined this with our fine-tuned claim verification model, and we got it to generate this stance label of supports, not enough information, or refutes. And if it generated it wrong, we considered it as a flagged entry because it should have been able to verify that fact as we'd expect. And we considered it wrong when it didn't match what was input in CIViC. So when we go and look at this, we need a way of telling, of these ones we've selected, are they actually wrong? And even if they are wrong, how many are wrong? And how does that compare to just randomly selecting things for review? So we've created this sort of pseudo metric by looking at the number of these CIViC entries in the freeze that we used for this, where they were pending revision. And we use that as they're probably something that should be corrected because the model was input the data before it was revised. And we can see this sort of gives us an idea that our model is probably working because we're getting about 7% pending revision in the non-flagged subset, whereas we're getting double that, 15% in the flagged. But how do you know, like, how much can we trust that? So my poor set of curators were given all 245 of the ones that were available in the full text to then go and review manually. And we found that approximately 35% of these had actual errors and things that should be corrected in CIViC. But also, we wanted to know what kinds of things we were actually detecting. So when we looked at the reasons, there were three main reasons that really stood out. And the first one is maybe something we should expect, but not immediately obvious, is that schema changes to your model as you learn more things you want to collect, or as your knowledge base evolves, like it did for CIViC, introduce things that even previously reviewed content then has to be gone back to and looked at. And we found that approximately 30% of the errors that were flagged by this model were from schema changes, such as the introduction of complex molecular profiles, which I'll get into an example of. Approximately a quarter of these were general human error. Somebody just read something wrong, or it just passed review because somebody assumed and didn't see the error that was there. The bulk of the errors were in specificity. So this means it wasn't totally wrong, but it was the wrong level of specificity. So often this applies to things like when you're saying what disease model should have been used for a cell line, or what disease a patient had, and it could have been a more specific entry into CIViC, or maybe it was too specific. So this is an example of something that was flagged by the error, or one of the complex molecular profiles that got flagged. So in this paper, this is a case report of a patient that was first treated with chemotherapy. They developed a resistance, or they developed a mutation in EGFR exon 19. They were then treated with erlotinib, developed resistance, and we see this acquired resistance mutation, T790M. Then they were treated with osimertinib. Now, what the evidence in CIViC was actually looking at was the response to osimertinib. So this had been input with just this T790M, but because there was no like control group with the EGFR exon 19 deletion, it really should have included both the EGFR 19 deletion as well as the T790M. So when we went through there, we were able to go and add this to the molecular profile. So this is more accurate representation of this association than previously. It also found things just like human error, where someone had put in the evidence direction as supports, and it should have been does not support. This might have been just that it was a default, or it could have been because of the wording here. So it's likely that when the curator was entering this into CIViC, they were doing multiple entries from the same paper. And you can see that in this paper, they say that the beta-catenin mutations, the S45F mutation was associated with response to therapy, but that the others were not. And earlier in the paper, they tell you which ones the others are, but it includes the one that was curated here, which is the T41A mutation. So this should have been entered as the ones where it doesn't have an impact. Now, this is all really useful, but one of the strengths of these large language models is their ability to explain. So how much more helpful would it be if the model not only told you something was wrong, but exactly what was wrong and how you should change it? We can generate these explanations with the LLMs, but evaluating them is a lot less straightforward. Many people use fully automated metrics like Rouge or bigram similarity, or even newer methods like LLM as a judge. But the only way to know for sure is to actually look at the data. And again, thankfully, I have some really good curators who are willing to do this with me. So what we did here is we took the results from this fact-checking pipeline. We took the evidence and the claim, and we input them into different large language models. We generated those responses, and then the curators were asked to review the responses. They were not told which model generated the response, and they were randomized in the order of the responses. We did this with 11 expert curators, and they were asked to flag potential errors. So we looked at many different things. We looked at whether content was helpful, and it should be pretty specific. It's not supposed to be just like, yes, the evidence works. Like, that's not really helpful. But we also looked at a bunch of different types of errors, like if it's a factual error, did the response say something that is incorrect based on the evidence or claim? Did it contradict itself? Was it coherent? Now, this is not as big of a problem as it used to be, but in the earlier large language models, or even earlier language models, things were pretty incoherent. One of the more interesting things we looked at was logical errors. And this is like, it makes a logical leap or assumption that may sound credible, but is actually incorrect. And then we also looked at what we are calling extra information. Now, these could be hallucinations or other things, just using evidence from the wrong paper, but because we've asked it to look at that particular evidence, these would be considered an error. So these results might not surprise you that much, that the proprietary models vastly outperform these smaller models. And this is even with the fine tuning. Now, I will with the caveat that there's only a small subset of our data set actually has the written explanations. So as we're collecting more of those, which we're currently doing, we do expect the fine-tuned model to improve quite a bit. But as it is right now, we would probably be going with one of the proprietary models for the explanation component, even though it did poorly on the classification component. What you see is that GPT 4.1 performs the best at about 83% of the responses were both helpful and did not have any errors. Now, one thing we did not look at was whether or not they were a complete response, but we will be looking at that later. But what does this actually look like? So I was really impressed by this example. This is from Gemini. And there was an error in the paper, actually, where they had put the wrong protein notation, but they put in the 3-letter codon notation and the CDS notation, and we were able to translate that into the correct notation. So when someone put this in CIViC, they put the correct variant. So what the model saw was the correct variant in the claim, and then the evidence with the incorrect variant. And of the models that we tested, Gemini was the only one to be like, oh, actually, I can translate that and check, and it actually matches up to the variant that should have been. So clearly those two match up, which was actually really impressive in my opinion. But they also can make really illogical leaps. And we're only showing the best performing models here, but I assure you the open models also make mistakes. So in this one, the evidence that was given to the models did not include the third drug. It included aspirin, cilindinac, but it did not include ibuprofen. So the claim did. The claim said that it was for all these 3 drugs. But the only reason GPT-4 is saying that it saw this in the evidence is because it just read the claim and said, yeah, it's there. It wasn't there. We also have things like this where it said that the preclinical data showed improved survival outcomes. But in this paper, they didn't do any organism level experiments. They just did tumor data. So you can't really show survival data from the tumor experiments. There's also this one here as an inappropriate generalization. So in Gemini, it says that because this claim was for the PIK3 amplifications, but the evidence only talked about alterations, not amplifications specifically, which is only a subset of the alterations. And Gemini says, that's okay. PIK3 amplification is a type of alteration. Therefore, this is evidence for alterations. But as as many of us know, there is a lot of other types of alterations that occur. And there's nothing in this paper to say that PIK3 amplifications even were one of the alterations they looked at. So what does this mean? Well, in conclusion, CIVic-Fact presents a challenging evaluation data set for both large language models and fact-checking pipelines. It is a successful proof of concept. We still have a lot of work to do, but we were pretty happy that we were able to get this to work in the real world. And that the human AI collaboration can help verify even these really complex variant interpretation knowledge is a huge step from where we were 10 years ago. One of the interesting things to come out is that we all know, and maybe I think Chris Mongol's talked about it a bit, but evolving schema changes in biocuration really create a lot of work for the reviewers. And you have to go back and look at previously reviewed content. And this could be a way to help because we thought the bottleneck was bad when we were reviewing submitted content. Having to go back to old content, also a problem. But even with the largest large language models, there's still room for improvement in justifying their decisions. I do not work in isolation. I am incredibly fortunate to work with the wonderful people at both the Genome Sciences Center in Vancouver, Canada, as well as the CIViC team in St. Louis. This work's been funded by the Marathon of Hope, Cancer Center Networks, the Canadian Institute for Health Research, and the University of British Columbia. The preprint will be out soon. It is not yet, but until then, you can contact me on LinkedIn if you like.
Thank you very much. Do we have any questions? So I can ask a question. Why do you think it is that you have the fine-tuned models actually working well on one task, but they don't work well for explainability, like on interpreting them?
I think it's just due to the size of the model. So the classification task, like it doesn't take you don't need as big of a model to represent a 3-class classification problem as you would to represent basically all the reasoning and all the language and knowledge that you'd need to put into an explanation. So I'm hoping that we get better, smaller models eventually, but at the moment, it seems like we really do need the larger models.
Have you got any thoughts of moving the fine-tuning process itself forward in the future, kind of improving it, redesigning it?
We did a pretty basic fine-tuning. Like I just took our data set and threw it through and just tried to do like the completion. But there's a lot of really cool work being done with like including ontologies in your fine-tuning training or including like question answering as you're learning about a paper that have been really exciting and cool. We just haven't had time to explore those kinds of things yet. Hopefully, once we release this data set, it will be public. Maybe someone will explore that if I don't myself before then.
Super, thank you very much.